All right, so if we're just picking up where we kind of left off yesterday, we kind of just did some introduction of terms. A solution being a homogeneous mixture. So I've got a physical combination of multiple substances, and there's a uniformity to the appearance. I can't pick out one component versus another. And so that led into kind of a interesting outlook as we were closing yesterday, where we could actually indicate some different kinds of solutions that were more than just, I take this solid stuff and I dissolve it in this liquid stuff and I get a liquid combination of the two. We started to think about things in terms of what a solute is versus a solvent. Solvent being the stuff that's in the greater amount, the stuff that actually does the dissolving, and the solute being the stuff that gets mixed in, the stuff that actually dissolves. And we talked about the idea of water as a solvent, where water as a solvent creates what are called aqueous solutions. And that's where we get into this idea of the polarity and a lot of the other concepts we've talked about thus far. Now, as far as the process is concerned, what we have to consider when a solution is formed is what is going on inside of the solution from the standpoint of the molecules themselves. So we know, because all things do this, that every substance has intermolecular forces. There are forces of attraction that exist between one molecule and other molecules in a sample. And sometimes those forces are really, really, really strong, and sometimes those forces are really, really, really weak. And we also know that when we combine substances, new intermolecular forces also can exist between the substances and each other. So I combine water with sugar, and not only are the water molecules interacting with water molecules and sugar molecules interacting with the sugar molecules, but the water and the sugar will interact with each other. Now, when a solution forms, those intermingling forces are better than the individual forces. So a solution happens when we get better interactions between the solute and the solvent compared to the solute by itself or the solvent by itself. And if we take that logic and flip it around, we can also explain why things don't dissolve. Why doesn't oil dissolve in water? Why don't we see organics dissolving with water? Well, because the forces are different. London forces are extremely weak. Hydrogen bonding in water is extremely strong. If I cross those over, hydrogen bonding interacting with London forces, nonpolar forces, it's not going to work because the hydrogen bonding is way stronger than the London forces. And so that's why they stay separated. And this is what we can kind of take all of that knowledge, all of that intermolecular forces stuff, and we can distill it down to a 3-word phrase. Like dissolves like. If I look at the intermolecular forces of the two things that are trying to combine, when they have similar kinds of forces, that means polar forces or non-polar forces, if the forces are similar, they dissolve. So polar stuff dissolves in other polar stuff. Non-polar stuff dissolves in other non-polar stuff. But if I try to cross them over, polar and non-polar do not interact with each other. Like dissolves like. Now we've kind of danced around this particular topic for a couple of weeks now. Especially when we're looking at how do the different functional groups interact with water. What is the solubility of an amine in water, an alcohol in water? But now we can state it more fully. Light dissolves light. And so when we get into polarity, that like dissolves like pretty much extends into anything with a charge. If I have a charged compound of any kind, a polar molecule like water will dissolve. And so when I look at an ionic compound like sodium chloride in its solid form has no free ions. We have a crystal that is composed of ions, but all those ions are attracted to other ions. But what happens is that the water molecules can start to surround that sodium chloride crystal, and through the attraction of those hydrogen bonds, those polar forces to those ions, it can actually start to separate, pull apart that ionic crystal. And the net result is we'll get what are called hydrated ions. These hydrated ions are ions, positive charges or negative charges, that are going to attract the opposite end of the water molecule. So sodium ion here is a positive charge, and it's going to attract the negative part of the water molecule, the oxygen. And on the flip side, the chloride, which has a negative charge, it's going to attract the positive end of the water molecule, which is the hydrogen. And the reason this happens is because even though ionic bonding is really strong, there is more attraction between this sodium ion and these other oxygen to the water molecules than what the sodium has with chloride. So it's kind of a collective force. I put together the attractions of that sodium with 4 or 6 or however many sodium water molecules it can attract. And the total amount of attraction between the sodium and those waters is greater than the attraction between the sodium and the chloride, so they break apart. Now, we don't have to do this with just ionic compounds. Any polar molecule will work in the same way. If I have methanol with water, we know methanol and water are infinitely miscible with each other. You can dissolve one into the other in any proportion, any amount. And the reason why is in both cases, we've got hydrogen bonding going on here. So I've got hydrogen bonding taking place in the methanol sample, hydrogen bonding taking place in the water sample. They hydrogen bond with each other to make a solution. So they naturally can just kind of attract each other because they have a similarity of force. So let's take a moment here. This is kind of review this first section, this kind of introductory section here in chapter 9. In each of these samples, I've got a couple of different components. We need to identify the solute in each case. So if I have 2 grams of sugar or 100 milliliters of water, which one would be the solute? It would be the sugar. And if I had 60 milliliters of ethanol and 30 of methanol, it'd be the methyl alcohol. And if I had 55 milliliters of water and 1.5 grams of salt, it'd be the salt. And if I had air, would it be the oxygen or the nitrogen? Be the oxygen. So the key thing that is key and common here, which you seem to pick up on, the one that is in the lesser amount is the solute. Always. Yeah, gotta love those absolutes. If it's in a lesser amount, it's a solute. If it's in the greatest amount, it's a solvent. And so there's only ever one solvent. So if I look at air, air is more than oxygen and nitrogen. We've also got carbon dioxide in there. We also have some other trace amounts of other gases. All of those except for nitrogen are solutes. Nitrogen is the solvent. There can only be one greatest. The thing in the greatest amount is the solvent. Everything else is a solute. Okay, if we have solid lithium chloride in water, why does it dissolve? What is attracted to what? As we're looking at how those water molecules and those ions interact. So which part of the water molecule would the lithium ion attract? So lithium is positively charged, opposite charges attract. So the oxygen atom would be what attracts the lithium. And so chloride ions, they're negatively charged. We would have them attract the hydrogen instead, because again, opposite charges attract. Like dissolves like, but opposites attract in terms of charge. All right, which of these will dissolve in water? Okay, let's think about our principle here. Like dissolves like. So is water polar or non-polar? Amelia, say that out loud. It is polar. So water's polar. So if we're looking for things to dissolve in water, we're also looking for other polar substances. So we're either looking for things that are ionic or things that we know to have electronegative kinds of pieces on them. So like oxygen, fluorine, nitrogen, sulfur, those kinds of things. Okay, so letter A, should that dissolve in water? It should. We should recognize that it's an ionic compound. I've got a metal and a non-metal in the same compound. That's a pretty good indicator that I'm dealing with an ionic compound. Ionic compounds generally dissolve in water, so yes. Should gasoline dissolve in water? Okay, know that one anyway, but now we have reason. Gasoline is primarily made out of octane. Octane is a hydrocarbon, and we know that hydrocarbons are non-polar. Water is polar, they don't match. Iodine. So is iodine ionic? Do I have a metal and a non-metal here? No. So we can cross that one off. Do I have a polar bond here? If iodine is bonded to itself, will it share electrons unevenly? No. So that's a nonpolar molecule as well. So, it's been a while since we talked about polarity from that standpoint. But remember, for polarity, we need to have a bond that has two different atoms on it and have a difference in electronegativity. With iodine, we have neither. We've got the same atom on both sides of the bond, and so obviously there's going to be no difference in electronegativity. Hydrogen chloride, HCl. Is it a metal and a non-metal? Not really. Even though hydrogen's with the metals there on the side, we know that hydrogen's not actually metallic. But is there a polarity in that bond? You can pull out the values. I believe chlorine is 3 and hydrogen is 2.1. So there is a difference in their electronegativities and a big enough difference to consider this bond polar. HCl does dissolve in water. When it does, we know it as hydrochloric acid. To answer the question why, the answer is pretty simple. Like dissolves like. The things that are highlighted are polar like water. The things that are not are non-polar and wouldn't dissolve in water as a result. All right, questions so far? Okay, so that was the first part. That was section 1. Now here in section 2, we're going to get into what are called electrolytes. Now, we've heard the term electrolytes thrown around in a number of different ways. Watch any sporting event, and there will inevitably be 6 different commercials on for Gatorade, Powerade, pre-workout, post-workout, you name it kinds of products. And most of them talk about their electrolytic powers and what they have that the other ones don't. That's all well and good, but if we don't understand what an electrolyte is in the first place, all that stuff is just going to sound like stuff. So how do we identify electrolytes and what do they actually do? So electrolytes are so called because they are solutions that will conduct electricity. That's why they are called electrolytes. They are solutions that are conductive. So hook your Gatorade bottle up to a light bulb and it will complete the circuit and light the light bulb. Now, as far as electrolytes go, we can break electrolytes down into 3 relatively consistent categories. There are the strong electrolytes. These are the electrolytes that when we have a substance that is dissolved in water, it 100% breaks apart in the water to form ions. We tend to see this with salts. We tend to see this with strong acids. So the example that's shown here, this is a solution of sodium chloride in water, salt water. And what happens to the sodium chloride is that before we mixed it in, it was a solid. After we mix it in, those water molecules pull that ionic crystal apart. We end up with sodium ions and chloride ions. And those sodium ions and chloride ions, those end up being what is able to stabilize the electrical charge to allow electricity to flow through it. And since we have lots of ions present, we get good conductivity. Let's compare that for a moment with weak electrolytes. They conduct electricity, but they do so poorly. So you look at that light bulb, you can see the light bulb's on. But it's like a light bulb on its last legs. All right. Good, Sean. So okay, so what's probably the most confusing about weak electrolytes is they all dissolve in water. Is what happens when they dissolve in water. That's kind of the mystery. So hydrogen chloride dissolves in water to make hydrochloric acid. That's what this AQ designation means. AQ stands for aqueous. Remember how we talked about water-based solutions called aqueous solutions? Now we see in this abbreviation where that term gets used. So all that this means is that this hydrochloric acid has been dissolved in water. Okay. Yes, because if it dissolves in water, it's aqueous. That means that it is part of the aqueous solution. So what sets these weak acids and weak bases apart is that when they dissolve in water, they don't always break apart into ions. We get some ions, but not many. And that's why the light bulb doesn't light up here as well. The intensity of that light in the light bulb has everything to do with the number of ions that are present. The more ions that are present, the more electrical charge can be stabilized, the more conductivity it has. The lighter the bulb is going to be. So in our strong electrolytes, which again, salts, strong acids, and I forgot to mention this, but we'll put it in now, strong bases. In this module, we see that every single one of these guys gets converted into ions. So there are lots of ions in the solution. In a weak electrolyte, the split is actually not that great. When this equilibrium kind of settles down into a normal position, what we'll see is that only about 5% of the molecules actually break apart into ions. The other 95% stay in this dissolved but molecular state. And in the molecular state, obviously it's not going to conduct electricity because there are no ions on this side of the equation. So because there are so few ions here, that's why we get a lower conductivity. And again, this is kind of an unusual phenomenon. Weak electrolyte behavior is generally limited to acids and bases that are considered weak acids and bases. Sean again?
All right.
Yes. Yes, if we're representing what are potentially ionic compounds, the positive ion goes first and the negative second. Okay, so this is the second category. Second category here, kind of limited in its scope. We're talking about either weak acids or weak bases. The third category, non-electrolytes. These are substances that do dissolve in water, but do not break apart whatsoever. So, great example of this is sugar, sucrose. When we put sugar into water, it doesn't conduct electricity because there are no ions in sugar. There's nothing I can break off of it to turn it into ions. So what we get in these are mostly molecular compounds. And within these, you would get things like organics. And biomolecules that are polar. So this is different from, say, octane not being able to dissolve in water. That's a different argument, a different kind of characteristic. We're still talking about stuff that dissolves, but it doesn't produce ions. So we're talking about things like alcohols, carbohydrates, some kinds of amines, amides, that generally don't give us a whole lot of ionic character, but are still soluble in water. So those are the three categories. Strong electrolytes. These are the things that break apart into ions, give us lots of ions, conduct electricity really, really well. You've got your non-electrolytes, stuff that don't ionize, stay completely molecular. And then you've got the weak electrolytes in the middle, which for the most part act like non-electrolytes, but produce just enough ions that we can notice that they conduct electricity. Alexis?
So when it comes to taking the iron,
Yes.
I need to basic.
Yes. So yeah, that's a good way to think about it. Strong electrolytes, we get all ions. Non-electrolytes, we get no ions. Weak electrolytes, we get some ions. And I mean, I guess this is more or less what this table is summarizing as well. So in this table, good thing to kind of take note of these weak electrolytes, these strong electrolytes, you can kind of see some examples in. So ionic compounds, these bases here are what we consider strong bases. I already talked about them a little bit, lye and potash. Sodium hydroxide and potassium hydroxide, and then acids that we generally consider strong acids: hydrochloric, hydrobromic, nitric, sulfuric. Your weak electrolyte category kind of covers the acids and bases that don't fit that description. So things like ammonium hydroxide or water. Water really doesn't have a true electrolyte character. It's still very, very, very weak. But things like acetic acid would be in here. Some of your other organic acids would fit into this description as well. And then non-electrolytes would be most of the organic compounds that we've talked about that have some water solubility that are not acids. Acids, organic acids fit into that middle category. But your organic alcohols, your ketones, your amines and amides, they would fit into this non-electrolyte category. Okay, so let's see what we can kind of pick up here. So in each case, we're looking at a strong electrolyte. So we know that we are going to be creating ions. Question is, what ions are we creating? So in number 1, we know that A is incorrect because as a strong electrolyte, it's not going to stay together, or in this case, not even dissolve. We know it's going to break apart into ions. What do those ions look like? Well, we know calcium ion is going to be one of them. The question is, what do we do with that 2 here? And the answer is letter C here. What we have to remember, and this is again going way back to when we talked about nomenclature, so all the way chapter 6, which seems like so long ago. What we have to remember, that 2 there is just telling us how many chloride ions there are. Since calcium is a 2+ and chloride is a 1-, I need 2 of those chlorides to match up the charges. So this ion doesn't make any sense, the Cl2 with a -1 charge. And the reason it doesn't make any sense is, think back to our fundamentals here. An ionic compound has to have charge balance. I've got a +2 here and a -1 there. I don't have a balance of charge. I have an extra plus. But if I look at it in the way that letter C is, where I've got a +2 charge and 2 -1 charges, now I've got 2 and 2. Now I've got charge balance. So with that in mind, what's the correct answer for number 2? We know it's not B. It's going to be A. Even if we don't know that the phosphate ion is PO4 with a -3, we know that this is the only one that makes sense from a charge standpoint. I've got a -3 for the phosphates, and I've got 3 +1s for each of those 3 potassiums. I've got a balance of charge. This doesn't have a balance of charge. This, letter C, is a bunch of nonsense. And a good way to kind of figure out nonsense is a recognition kind of thing. It's been a while since we went back to chapter 6. But nowhere in the past 11 weeks have I told you anything about an ion that looked like this. When we're looking at ionic compounds, they should always make sense. 4 oxygens with a -1 charge total, that doesn't make sense. 3 potassiums with a 1+ charge total, it doesn't make sense. Where does that positive charge come from? Does each potassium have 1/3 of a positive charge? Doesn't really make sense, doesn't add up. Which of the following would represent a strong electrolyte in water? So we got to think back, what does the strong electrolyte show? Strong electrolyte is going to show what as products? Charges, ions. There's only one reaction here that shows ions as the product. It's letter C. If I have a strong electrolyte, I'm going to have ions present to stabilize and conduct that electricity. Doesn't work otherwise. So I will warn you, if you read through section 2, there is some additional stuff in there. They talk about some calculations that you do regarding something called equivalence. Don't worry about that. Skip over that part. All that we're really looking at out of section 2 is, can you classify substances into electrolyte versus non-electrolyte? And can you identify what happens when ionic compound breaks down to its ions? That's what you need to know. So all of that stuff in here about equivalence and turning calculations are coming, but not that kind. All right, solubility. So insolubility, what we're going to be looking at are what are kind of the characteristics that allow us to not only just determine whether or not something dissolves, but what are the limits in terms of how much can dissolve. That's ultimately what solubility is about. And a real world example of that is something called gout. Gout comes as a result of an overabundance of uric acid in your blood. If the concentration of uric acid in your blood exceeds 7 milligrams per 100, then you will experience what is called gout. Gout is this kind of painful inflammation kind of I don't even know what to call it, a blood disease necessarily. Bottom line is it doesn't feel good. And so solubility limits exist in a number of different circumstances. Gout is one example of kind of a human health kind of circumstance. But even if we're talking about solutions, solubility does carry limitations. Things that we consider to be soluble are not going to be soluble forever. There is going to be a limit to how much we can add. Now, there are some exceptions to that. We talked about water and alcohol, water and methanol being infinitely miscible. Yeah, that's an exception. That's not usually what happens. Usually what happens is we have some kind of limitation that takes place. That's what solubility is. Solubility tells us the maximum amount of solute that can dissolve in a given amount of solvent. And it is a temperature dependent kind of idea. Increase the temperature, the solubility is going to change. Decrease the temperature, the solubility is going to change. And you kind of already know this. You're at home, you make tea. You put the sugar in when the tea is warm because you're smart. Then you throw in a whole bunch of ice and maybe some of that sugar kind of falls out and settles on the bottom. Why? Solubility. At a higher temperature, you can dissolve more sugar into the tea. But when you drop the temperature down, you start to hit that solubility limit, and the extra sugar that you added that fit when it was hot doesn't fit when it's cold anymore, and it settles out. We can express solubility in terms of grams per 100. Grams per 100 grams of water is usually the definer. Sometimes we'll see this as grams per 100 milliliters instead. For water, it really doesn't matter because of the density of water being 1. When it comes to solutions, there are 2 different classifications that we can use. We have what's called the unsaturated solution. This is the solution that we had at the beginning, where we had our hot tea and we added sugar to it and the sugar dissolved. Unsaturated solutions have a concentration under the solubility limit. And as a result, so long as we stay under that limit, we can continue to dissolve more solute into that solvent. So I got my hot tea, I add a cup of sugar, it stirs around, it goes in. I go, maybe I want some more. Put in another cup of sugar. If it all dissolves, that first solution was considered unsaturated because it was able to dissolve more sugar. So long as we are able to continue to dissolve more, the solution that we have is considered unsaturated. Okay. That's what we're getting to. There's a solubility limit. Every substance has a solubility limit in water. It does differ substance to substance. So the solubility limit for table sugar is different from table salt. It's different from sodium hydroxide. They all have different values and different numbers to them. But at some point, we can't add any more. When we do, and it doesn't dissolve, the resulting solution is considered saturated. It's got as much in it as is possible. And anything extra would just fall down to the bottom of the container, would not dissolve. Okay, I was hoping for something a little bit better than that. Okay. So here is an example. Your book has a listing of these values, or so I thought. Oh, they've got a graph. Which isn't nearly as much fun to look at. Right, so this is overkill. But we can point out a couple of key ideas here. So sodium chloride, NaCl. What we can see is that, for 20 degrees Celsius, which is right here, this is kind of our normal room temperature. We can get about almost 36 grams of sodium chloride into 100 milliliters of water. That's its solubility limit. But what we can see also on this table, and again, it's easy to get lost in kind of the minutia here, is that there are different values for different substances. So sodium chloride, we know, dissolves pretty well. Sodium hydrogen carbonate, baking soda, we can see doesn't dissolve nearly as well. 9.6 grams per 100 instead of 36 grams per 100. So different substances do have different amounts, or excuse me, different solubilities to them. Sucrose, on the other hand, I mean, that's a lot. 201.9 grams per 100. Technically speaking, you can add sucrose until it becomes the solvent. So yes, to answer kind of the general question, these values do exist. You just gotta know where to look. But they also do tell us a whole lot about kind of what's what. And we can see that there are temperature effects. So generally speaking, at least for solids, we increase the temperature and the solubility increases with it. Decrease the temperature, solubility decreases in turn. And things that we kind of already knew. Go back to that iced tea example. Go back to pretty much any type of solution you would make at home for whatever reason. It's gonna be a heck of a lot harder to dissolve something in ice water than it is in hot water. But there is a limit to all of them. That limit is called the saturation limit. That solution is called saturated as a result. All right, let's look at each of these solutions and figure out, are they saturated or unsaturated? So if I put salt into water and it dissolves, how would we describe the solution? It's going to be unsaturated. And the reason we know it's unsaturated is because the salt dissolved. If it were saturated, it would be like letter B. Where we take sugar into water, we attempt to stir it up, but it all settles to the bottom. No more sugar can dissolve, which must mean that we are at the saturation limit. It's a saturated solution. Right, go ahead. So if you took it to the exact limit and no further, technically that would be a saturated solution. Now, visually speaking, you wouldn't be able to determine if it was saturated or unsaturated until you tried to add more to it. But if we took exactly 100 grams of water and added exactly 201.9 grams of table sugar to it, I think so. I'm going off of memory from just 2 minutes ago. But if we took those exact amounts and added them together and all of it dissolved, and believe me, it would take a while to do that. When you get near the saturation limit of a solution, it can be really hard to get those last few bits to dissolve. They will eventually, but it's not going to be one of those that turn it over and it does it in no time kind of things. But yes, that solution would technically be considered saturated. But we would have no way of actually proving it until we try to add that next spoonful and find that it didn't dissolve. Okay, got to do a little bit of math for this part, at least for some of these. At 40 Celsius, the solubility for potassium bromide is 80 grams per 100 grams of water. Identify these solutions as either being saturated or unsaturated. Now, in part A, this was actually pretty easy. We have exactly 100 grams of water, and we can see that 60 is less than 80, which is the limit. So this would be unsaturated. I can put an additional 20 grams in there and it would still dissolve. With parts B and C, now it gets a little bit more interpretive. So I got to do a little bit of math since I don't have exactly 100 grams. So I've got 200 grams of water, and I try to add 200 grams of potassium bromide to it. Well, the way to get to this, to have something to compare, would be to turn the water into 100 grams and then do whatever the calculation that you did to the water to the kVr. So if I divide each of these by 2, I now have 100 grams of water and 100 grams of potassium bromide. I can see that 100 is greater than 80 this time. My saturation limit is 80. I've got 100. So 20 of those grams aren't going to dissolve. This is going to be a saturated solution. And I can make a similar argument with the 50 grams of water. If I multiply it by 2 to get 100, I'll need to multiply the 25 by 2 to get to the 50 grams of potassium bromide. 50 is not as much as 80, so there is more room in there for adding more potassium bromide if I wanted to later on. But the other key attribute there is we had to know that all 3 of those temperatures were 40 degrees. Because that value for the solubility is only true at 40 degrees. Take that down to 35, take that down to 20, take that down to 10, move it up to 75, we're going to get different values each time. Solubility is incredibly temperature dependent. Incredibly temperature dependent. All right, questions with this? Okay. Now we're getting into the most difficult section in this chapter. And the reason why it's the most difficult is because it's the most involved. We've got lots of calculations in here. And what my goal is for today, we're going to focus primarily on the percent-based calculations, and we'll save the other ones for Thursday. Now, concentration is an important idea for us because it gives us a way of quantifying how much solute is in a solution relative to the total solution or relative to the solvent. Gives us a real good idea of proportion. When we're doing chemical reactions or when we're monitoring different kinds of body systems, that percentage, that ratio is really important. So we have to have some ways of quantifying that other than just high, low, okay. Concentration values are generally a ratio, meaning I've got some kind of fraction, a numerator related to the amount of solute, a denominator related to the amount of solution usually. And as far as they go, there are 4 ways that we're going to look at concentration. First 3, these percentage-based ones, I've clustered them together because basically the calculation looks identical. It's just a matter of what's on the top and what's on the bottom. And luckily for us, the name of them tells you exactly what's on the top and the bottom. A mass to mass percent, well, that's exactly what you think. The mass of the solute divided by the mass of the solution. Volume, milliliters of solute, milliliters of solution. Mass volume, well, mass of solute, milliliters of solution. And each one of these are percentages, which means they each get multiplied by 100%. So for mass percent being the ratio of masses, again, we're looking at how many grams of solute compared to the total number of grams of solution. And so sometimes we will be given the individual masses. So 30 grams of sugar and 50 grams of water. And yeah, in that case, we would add those together to get the total solution. Sometimes we are just given the total mass of the solution. So when that's the case, we just plug that into the denominator. We don't need to figure out the individual masses along the way. There are occasions where we might need to use this as a conversion kind of ratio. And basically all that this equation is just a percenting of this equation. So if I want to know how many grams of water are in a 3% solution, well, I can use this to figure out how many grams of solute there are, how many grams of solvent there are, just by breaking it apart. So, an example. When water is added to 8 grams of potassium chloride to form 50 grams of a potassium chloride solution, the mass percent concentration is 16.0%. How did we get that? Well, it's exactly what we just talked about. The percentage, mass over mass, would have been 8.00 grams of KCl divided by 50.00 grams of solution, since we knew the total solution value, times 100%. 8 divided by 50 times 100 gives us that 16.0% potassium chloride. No, because in the third case, mass volume percent, you won't have the same units, but you'll still multiply by 100. Yeah, that's what makes it a percentage. Percent literally means parts of 100. So the ratio is telling you kind of the fraction, how much of this substance is the solute. Multiplying it by 100 takes that fraction and converts it to a percent. Okay. Well, if we don't get to it in the next 10 minutes, we'll definitely get to it Thursday, I'm sure. Now, this is a breakdown of a different form. Again, we didn't have to do this middle step because we already knew the mass of the solution was 50 grams. By doing it this way, we kind of skipped that middle step in between. Now, could we have come up with it on our own? Absolutely. If I have 50 grams of solution and 8 of it is potassium chloride, then logically speaking, the other 42 had to have been the water. But I don't actually need that to do the calculation for mass percent. From a stripped down kind of standpoint, I need the mass of solute. I need the total mass of the solution. If I can get it in one step instead of two, I'm going to take it in the one step. It's just about how the procedure works. So yes. So you're always going to multiply by 100 in the math so no. We'll get to it, but if you have a certain number of grams dissolved in a certain number of milliliters, you can still divide those two values and then multiply by 100% to get the percentage. Yes. All that'll tell you is that in 100 milliliters of that solution, whatever the percentage is, that would be how much of the solute would be in there. So if I have a 5% mass by volume solution of sodium chloride, that means that in every 100 milliliters of solution, there are 5 grams of sodium chloride. But I don't need to have exactly 100 milliliters of solution to figure that out. If I have 50 milliliters of that solution, it would still work out. It would just be that there are 2.5 grams instead of 5 in there. The ratio will always work out. It's the interpretation that will change based upon what that denominator is. All right, in lieu of doing these study check questions, which we'll start with those on Thursday, let's just go through the other 2 percentage calculations here, just so that we kind of can at least cover all 3 of them conceptually, which should allow you to do your homework. So volume, it's the same kind of idea that we saw with mass. The only difference is instead of grams in the numerator and grams in the denominator, it's milliliters in the numerator and milliliters in the denominator. Basically, nothing has changed otherwise. Now, why would we do this kind of calculation as opposed to the one that we just did? Not every solution is solid in the liquid. This works really, really well if I have 2 liquids that I'm mixing together. Because it's a lot easier to measure the volume of a liquid than to measure the mass of a liquid. And you've done both in lab, you know I'm right. It's easier to pop out a graduated cylinder, measure out 10 milliliters, than it is to weigh a beaker, pour it until I get exactly 10 grams, and then stop, and then go, oh, that's 10.01. Take your dropper out and pull out that extra little bit. It's a lot easier to measure volumes of liquids than it is masses. So that's where this kind of ratio can really be useful to us. Interpretation is exactly the same. The only difference is that percentage represents the amount of solvent, or excuse me, the amount of solutes in 100 milliliters of solution, as opposed to 100 grams of solution. And mass volume percent, again, the same kind of idea. We see mass volume percent used a lot for aqueous solutions, because again, it's easier to measure out that 100 milliliters of water or that 100 milliliters of solution than it is to try to weigh everything out individually. But the core idea is still the same. Mass on the top, volume on the bottom, multiply by 100. The percentage represents the mass of solutes in 100 milliliters of solution. All right, let's go back to that example then. A solution is prepared by mixing 15 grams of sodium carbonate and 235 grams of water. Calculate the mass percent of the solution. Okay, in this case, we've been given solute, which we know to be the sodium carbonate because it's in the lesser amount, and solvent, which we know to be water because it's in the greater amount. Before I break into doing any kind of calculations in related to that percentage, I want to figure out the total mass of solution. 15.0 grams of sodium carbonate plus 235 grams of water would give me 250 grams of solution in total. This is going to be my denominator. So mass by mass percent is going to be equal to the grams of the solute, 15.0 grams of sodium carbonate divided by 250 grams of water, or excuse me, of solution. Multiplied by 100%. $15 divided by 250 gives me 0.060. Multiply that by 100. And I would get 6.00% sodium carbonate, which would be letter C. Now, an important note, kind of as a closing remark here, anytime we give a concentration value, we want to make sure that we do two things. First of all, we want to make sure that we've got the unit on there, which in this case would be the percentage. And we want to make sure that we represent what the solute is. In this case, the sodium carbonate. We want both there because we want to be specific. It's this percentage of this solute. Where that covers us is in the event we've got multiple solutes. That tag on there tells us, okay, it's 6% sodium carbonate and 1.3% sodium chloride, or whatever. If there are multiple solutes present, they would have different concentrations, probably. Not always, but probably. And for from that standpoint, we would want to make sure that we are specific in saying, okay, this is what this percent represents. It represents this solute. It's also important because you can do this same kind of percentage calculation with the solvent. So if I wanted to describe this solution as 94% water, that would be accurate. If I need to be specific in my values there. So on Thursday, we will pick up talking about molarity, which is the fourth kind of concentration and the most involved calculation, because not only do we have a ratio, but we have an additional calculation step to figure out the number of moles, which is something we haven't touched on in a long time. So we're going to need a minute to kind of rehash that. Have fun in lab. I'll see you Thursday. Have a good day.